The hunt continues for the mathematics behind computers. In this video, we're going to dissect a mathematical structure that rears its head again and again, the matrix. This structure is found all over discrete math and computer science and is the backbone of artificial intelligence. Today, you will navigate the structure of the matrix, learn useful matrix operations, and work through some examples to cement your understanding of this mathematical structure. So without further ado, let's just jump right into it. At a high level, a matrix is simply a group of numbers arranged into a rectangle. Every matrix is made of m horizontal rows and n vertical columns. A matrix can be many different sizes: 2 by 3, 5 by 1, 1 by 4, 3 by 3, etc. To access any given element of a matrix, you'll often see this notation with a lowercase variable and an ij, where I represents the row and j represents the column. A matrix where m equals n, like this 3 by 3, is called a square matrix. Square matrices, like their geometric brethren, have a number of interesting properties, such as having a discernible diagonal. If rows and columns are the ribs supporting the body of a matrix, then the diagonal of the matrix is comparable to its spine. In many matrices, the diagonal spine is the only part of the matrix with values other than 0. In other situations, the exact opposite occurs, where the diagonal is populated with zeros and often represents some distance or spatial data, such as the number of hops between routers, the distance between travel destinations, how amino acids fold in proteins, or whatever area of study needs a spatial representation. But before you can run headfirst into machine learning and cutting-edge research, you must first walk with basic matrix operations. We'll be talking about addition, multiplication, and exponentiation, matrix transposes, and matrix boolean operations. Addition between two matrices is done element-wise, so each element is added to each element. This means, to add two matrices, they need to be the same dimension. So let's say we have a matrix A equal to 3141, and B equal to 2072. A plus B equals the matrix C, with values 3 plus 2, 1 plus 0, 4 plus 7, and 1 plus 2. Like the addition you learned in your arithmetic class, matrix addition also has certain properties. First, it's commutative. So in our above problem, A plus B equals B plus A. As you can see from the animation, if we rotate the problems along the plus signs, we still get the same matrix C. Matrix addition is also associative, so if you add A plus B plus C, you could instead add A plus B plus C and get the same answer. Finally, matrix addition supports the identity property, where matrix A plus 0 equals A. In problems like this, 0 represents a matrix the same size as A, populated by zeros. We'll call these addition properties of matrices Theorem 1. Matrix multiplication is a bit more complicated. Instead of being done element by element, like addition, it's done by column and row. Let's look at how you can multiply this matrix A and this matrix B. First, you need to make sure that the internal dimensions of the two matrices you're multiplying are the same. Here, A is a 2 by 3 matrix, and B is a 3 by 2 matrix. so you know they can be multiplied together, because the first matrice's number of columns is the same as the second matrice's number of rows. You now also know the result of our multiplication will be a 2 by 2 matrix. So let's calculate the first element of this 2 by 2 matrix. The value you want to fill is C1, 1. So grab the first row of A and the first column of B. You then need to multiply the first element of A with the first element of B, and then add it to the product of the second element of A and the second element of B, and then add that to the product of the third element of A and the third element of B. Formally, C at ij is equal to the sum of A at ik times B at kj, where k is iterating through every element of row I in A and every element of column J in B. This demonstrates both why the internal dimensions of A and B have to be the same, and why the outer dimensions define the size of the resulting matrix C. Let's calculate C1, 2 together. We're still in the first row, so we grab the 3, 1, and 4 from A, but now we're in the second column, so we grab the 6, 3, and 8 from B. We then go element pair by element pair, so 6 times 3 is 18, 1 times 3 is 3, 4 times 8 is 32. Add them together, and we calculate the number at C12 is 53. We here at the Synthenomicon leave the bottom row as an exercise for the viewer. Matrix multiplication also has properties. It's associative, so A times B times C is equal to AB times C, and it's distributive, so A times B plus C is equal to AB plus AC. A plus BC equals AC plus BC. We have two different distributive rules because matrix multiplication is not commutative. AB does not always equal BA. Finally, matrix multiplication has its own identity property. A times I equals A. In this case, the I is called the identity matrix, and it's a diagonal matrix, where the diagonal is 1s and everything else is 0. We'll call this collection of multiplication properties for matrices Theorem 2. One special case of matrix multiplication is exponentiation, where you calculate a to the power of p, which is equal to matrix A times p number of itself. This is very similar to the exponentiation rules you learned about in arithmetic class. A to the 0th power is the identity matrix of the same size. A to the power of p times a to the power of q is equal to a to the power of p plus q. And a to the power of p to the power of q is equal to a to the power of p times q. Dimensions are important to using matrices effectively in computation. As you go throughout this course, you'll see a multitude of examples where changing the dimensions of a matrix is useful to solving a snarl of a problem. The most basic way to change a matrix dimension is to use the transpose operation. The transpose operation simply flips the matrix on its side. From an index perspective, every element in A at ij is mapped to A transpose at Ji. So these matrices, A, B, and C, have transposes that look like this. Notice how C doesn't actually change. When matrices don't change after a transpose, they're called symmetric. So every element C at ij is equal to C at ji. Transposes also have their own properties, which we'll call Theorem 3. First, A transpose is equal to A, so the transpose is considered to be an involution, like the complement of a set. The transpose also has distributive rules for both addition and multiplication. Note that when multiplying, we have to flip the order of A times B. The last species of matrix you'll see today is called the Boolean matrix. Boolean matrices are matrices that only have ones and zeros. This means, instead of doing Boolean operations one at a time, we as programmers can use matrices to do several Boolean operations in a single cycle. A Boolean OR operation results in a join, and it works in an element-wise fashion. So, Boolean matrix A or Boolean matrix B defines Boolean matrix C, where C at ij is 1 if A at ij equals 1 or B at ij equals 1. If both A at ij and B at ij are 0, then so too is C at ij. Similarly, a Boolean AND operation results in a meet, and it works in the same element-wise fashion as OR. So the calculation Boolean matrix A and Boolean matrix B defines Boolean matrix C, where C at ij is 1 only if A at ij and B at ij equal 1. Otherwise, C at ij is equal to 0. Both of these operations only work if A and B are the same size, and you should pay special attention to how the OR operation has strong similarities to the union operation in sets, and how the AND operation has very similar properties to the intersect in sets. The final operation is Boolean matrix multiplication. Like the earlier matrix operation, this works using rows and columns. Instead of each element being multiplied and added together, Boolean matrix multiplication ANDs each pair and then ORs all the pairs. This is called disjunctive normal form. So as long as a single pair of ones exists in the row and column under consideration, then C at ij is 1. Otherwise, C at ij is 0. Let's begin an example together, using these two Boolean matrices, A and B, to compute C at 1, 1. We grab the first row of A and the first column of B. We then AND each pair together, giving us a 1 and 1, or 1 and 0, or a 0 and 1. This simplifies to 1 or 0 or 0, which simplifies to 1. Thus, C at 1, 1 is 1. Let's look at one more example at C 2, 1. We grab the second row of A and the first column of B. We then AND each pair, giving us 0 and 1, or 1 and 0, or 0 and 1. This simplifies to 0 or 0 or 0, which becomes 0. Thus, C at 2, 1 is 0. Once again, we leave the completion of this matrix operation as an exercise for the viewer. The final Theorem 4 deals with these Boolean matrices operations. Both or, as well as and, are commutative. So A or B equals B or A, and A and B equals B and A. All three operations are associative. So A and B and C equals A and B and C, with OR and Boolean multiplication following the same pattern. Lastly, the AND and OR operations are distributive, and they follow the same pattern as unions and intersections in sets. So, A and B or C equals A and B or A and C, with the OR version being A or B and C equals A or B and A or C. You've covered a great deal of material today, so be sure to check out the practice problems linked below to really cement your matrix knowledge. Today, you learned about the incredibly prevalent mathematical structure known as the matrix. This rectangle made up of rows and columns of numbers is used everywhere in modern computation, from playing a video game to advanced AI. All of it runs on matrix math. You're still a long way from understanding all the math that goes into a computer, but I want to congratulate you on taking the next step with discrete mathematics.